Hello, sir. Actually, this assignment is in regard of the DA1 for the course of basic structural design, and I have taken a problem regarding two-way slab for the digital assignment. So the question is like design an interior slab of size 3 meter width and 4.50 meter height, simply supported on 230-meter thick beams. The slab is carrying a floor finish of 1.25 kilonewton per meter square and an imposed load of 5 kilonewton per meter square. Use M25, the grade of concrete is M25 and the grade of steel is Fe415. So Fe415 steel, and we should assume mild exposure. So first we'll note down what are the given conditions. First one, the dimension is 3 meter into 4.5 meter with thickness of 230 millimeters. And the dead load applied to the slab is 1.25 kilonewton per meter square. And the imposed load will be 5 kilonewton per meter square. And the grade of concrete we use is M25. And the steel grade is Fe415. And we're going to assume the exposure to be mild exposure. So what is the first process? We will find out the design. So to find out the design, we are taking Ly, that is uh, the width, I mean the dimension in y axis and the dimension in x axis. So whichever basically whichever is greater divided by whichever is lower. So here 4.5 is greater, so 4.5 divided by 3, which will get 1.5, will get to be 1.5, which is obviously less than 2. So we assume this to be a two-way slab. Suppose, just in case if it is greater than 2, then we'll take the problem to be a one-way slab and we'll proceed to solve the problem in a different manner. So from now we'll move on to the step 2, which is dimensions. So while moving on dimensions, first we'll assume the breadth of the slab to be 1000 millimeter. Then span by D is 32 into 1.25. Then from that D value, we'll get to be 3000 divided by 40, which we will get the answer to be 75 millimeter. So now moving on, clear cover, we always take it to be 20 millimeter. And the diameter of the bars, we take it to be 8 mm. So using this clear cover and the center of the bar, we'll find the value of D dash. So D dash is equal to clear cover plus the diameter of the bar divided by 2. So we get it to be 24 millimeter. From this diameter of the bar, we'll take it as to be small d. So now we have the value of small d and d dash. So using these both, we can find a value of capital D. So that capital D is small d, uh, I mean 75, that is a small d, plus 24, that is d dash. So we get it to be 99. So the nearest rounded off value will be 100 millimeter. So we take the capital D value to be 100 millimeter. So now finding dx in the diameter in terms of x axis and diameter in terms of y axis. For x axis, we just take the capital D minus the d dash. So you get 76. For dy, we take capital D minus d dash minus the diameter of the bars, from which we get 68 millimeter. So from now, we have completed the second step and first step. We are moving on to the third step, which is analysis of beams, analysis of slabs, analysis of the slab. First we take dead load. Dead load is given in the question, 1.25 kilonewton per meter square. And self weight is 0.1 into 25, which will give 2.5 kilonewton per meter square. And the imposed load is also given in question, which is 5 kilonewton per meter square. So total load is basically the sum of all these imposed load, self weight and dead load, which will get 8.75 kilonewton per meter square. So now there are two important formulas before we plot down the table. First one is moment in terms of x-axis is alpha x w into Lx square, and moment in terms of y-axis is alpha y w and Lx square. So we take the plot the table. First one is component. and we divide the thing into short span and long span. Under short span, we'll have support and span. Under long span also, we'll have support and span. So, okay. So first one, diameter. Diameter, we have already found it to be 76, dx to be 76. So we take that 76 value. And for long span, we already found it to be 68. So 68, 68. We take 76 for the longest span, shortest span, and 68 for the longest span. So next one, alpha value. Alpha value, we directly take it from IS456. So for each thing, it varies 0 0.053, 0 0.041, 0 0.0032, 0 0.024. So using this alpha value, we can find out the moment. Moment is basically alpha into W into Lx square. So alpha value varies for each column. So the answer for moment also will vary as per alpha. Otherwise, W and Lx square remains same for entire thing, entire row. So from now we already found moment. So with the moment we can find ultimate moment. So ultimate moment is basically 1.5 times the original the normal moment. So when we multiply, we'll get these values. We multiply 1.5 with this moment, we'll get these values. So next one, we take MUL by BD square. This value will get directly from SP16. So with this value, if we multiply B and D square, this BD square and that BD square will get the other BD square will get cancelled. So we get MUL value. So this MUL by BD square, we have to multiply a B is 1000, D is 76, 76, here 68, 68. So if we multiply, we'll get the answers. So as mentioned, the D value is 76 and same for this both. So we get the same answer here. And it's different for same for these both. So we get same value. And this both it's different. So we get different values. So we're checking if MU is less than MU comma L for everything. Since it is actually less, we take a single reinforced. If it is not less, we'll take it to be doubly reinforced. So since all the values for all the four are less than mu comma L, mu is less than the conditions are getting satisfied. It take it to be singly reinforced. Now we are gonna find mu by bd square. We have mu value and bd square also value also we have. So when we substitute in each place, we will get these values. mu is this value, and b is 1000 and d is respective 76, 76, 68, 68. PT value we'll get from IS456. So accordingly we'll substitute over here and get it. So AST, we have a formula. Using PT, we can find AST. So AST is equal to PT into BD by 100. So using the formula, we get these values. So AST minimum will calculate 0.0012 into B into D. That is a formula. So using that, we get 120 millimeter square. So the governing AST is 2 for it's like these values. So the spacing of 8 mm spacing we are finding 200 mm, 250 mm, 300, 400 mm. So maximum spacing also we are finding. This is a maximum spacing value. So with that maximum spacing value, we are providing a diameter of the bar and spacing. 8 mm, the entire thing is having 8 mm center to center with 200 mm bar. Only the position is changing. So AST provided whatever area of steel we have provided, we are writing it down here. So we are calculating the PT value for this AST provided. So earlier we discussed a formula AST is PT into BD by 1000. So if we keep PT in one side and take the rest to the other side, we'll get to know the PT value, which is here. So using the AST provided value, we are finding what is the PT value. So since we have already made this table now and we have already checked all these steps, now we will move on to shear check. To find the shear, there is a formula called 0.5 Lx minus D into W. So when we substitute these values here, Lx is 3, and D is 0.68 and 0.68 and W is 8.75. So you get 12.58 kilonewton per meter. So now we are finding ultimate shear. As now known, for finding the ultimate shear, we'll multiply the normal shear into 1.5. So we'll get 18.8 kilonewton per meter. So tau V values VU by BD. BD we know 1076, 68. So VU value we have just calculated. So we'll substituting, we'll get 0.2768 per meter square. So from table 19, IS 456 2000, tau C is equal to this 0.3236 Newton per millimeter square. So tau C is greater than tau B. So we can declare that this design is safe and shear. So last and final step for understanding all the calculations, we are checking for deflection, whether it can tolerate the deflection or cannot tolerate the deflection. So to find that, we are finding a span by D, which is 3000 by 76, 39.47. And Fs is equal to 0.58 Fy AST required as per syllabus. So 0.58 into 4.15 into 245 by 251. So the value will be 235 Newton per millimeter square. So the modification factor is 2.0. This 2.02. This we are calculating from figure 4. There will be a graph. In the graph, we'll understand where the point is getting plotted, and at the point between the point and the curve which is already there in the graph, we'll get the modification factor value. So at span by D, that is 32 into 62, we'll get 64. So we can declare that the design is safe in deflection. So since it is safe in deflection and it is safe in shear, we can say that this design is good and we can proceed to execute the design in real world circumstances. So this is the diagram for the design. So thank you, sir. This is the assignment for this is the two-way slab. I have explained the two-way slab in regard for the digital assignment. So thank you.